Hey, in our last lesson, we spoke about the limit definition by Cauchy, and we understood what's epsilon's role in the definition and why the definition seems to be so complicated. We showed that 0 is the limit of the sequence 1 over n, and we did that by showing that we can bound the elements of the sequence for any arbitrary epsilon. Now, it might seem we can do this with any sequence and show that any sequence has a limit, but I assure you, that's not the case. If a sequence does not have a limit, we would not be able to use Cauchy's definition to show that it has a limit. And this is going to be exactly the topic of this lesson. To do so, we're going to recall a sequence we already seen before, -1 to the n, an important sequence that we saw already in the introduction, and we know how it looks like. It's -1, 1, -1, and so on. In order to understand my point, let's go backwards. Let's try to prove that -1 to the n does have a limit. What that limit is, we can argue about it. Maybe -1, maybe 1. Let's go for something in the middle, 0. Let's try to show that 0 is the limit of this sequence. If that's what we're trying to do, then we need to prove that for any arbitrary epsilon, I can find an index, let's call it n naught, that for every n that is greater than that one, an would be bounded between -epsilon and epsilon. So I'll choose the following epsilon, 1.2, although I know epsilon represents a very, very, very small number. But just to understand the point, let's start with a large epsilon. In this case, I can find an element, actually the first one, the first term in this sequence, that from that point on, all of the rest of the elements in our sequence will be bounded between -epsilon and epsilon. And that's exactly what we're trying to do. That's exactly what the definition says. Given an epsilon, find the index. But the definition also says that we need to find an index for every epsilon. What happens if epsilon is smaller? So let's examine that case, where epsilon is a smaller number than expected. And let's look for that element, the one that from that point onwards, all of the rest of the elements are bounded within this new range we created. We can't find one. If we focus for a second on the index n equals 2, and we look at A2, A2 is above epsilon. Not only that A2 is above epsilon, all of the rest of the elements after A2 are either above epsilon or below -epsilon. Not even a single element is within the domain that we desire. So what do we usually do in this case? Well, we go further. We look for a larger n, that maybe from that point onwards, the rest of the elements will be bounded within that range. So let's try our luck. Let's go to n naught equals 11. But what do we see? That's also outside the range. It's smaller than -1. What about trying n naught equals 12? Well, again, same thing. It's 1 outside our range. What if we try 13 or go even further to 20? Does it even make a difference? Well, we see quite clearly that in this sequence doesn't matter. Doesn't matter how far we'll go, we will never find for our specific epsilon the index from which happens what it is that we want to. It's needless to say that if epsilon is even smaller, then we won't find that index. And that is exactly the reason why 0 is not a limit. So we can ask ourselves this following question. Did we just choose the wrong limit? Does this sequence have a limit that we just chose poorly? Well, we can give it a try. We can try giving -1 the option to be the limit of the sequence. We take one epsilon step up from -1, and we'll take an epsilon step down from -1. And we notice something quite interesting happening. A1 is within this range. Not only A1, also A3, A5, A7, and so on. An infinite number of elements are within this range. But just the same, we have an infinite number of elements that are outside this range. A2, A4, A6, and so on, that equal 1, all of them are outside that range. Now, it doesn't matter how far we'll go, whether we'll be at A11, A12, or A100, we'll never find an index that from that point on, all the elements would be within this range. Now, I think it's also needless to say that if we choose a smaller epsilon, things don't really change. It's kind of constant. But we can also notice something interesting. We have something that kind of looks like a limit at -1 and at 1. Both of them resemble a limit, but those are not exactly limits. Those are partial limits. And we'll discuss partial limits when we'll talk about subsequences in our next videos. So, see you then.